Oh, hey man, did you finish the homework? I was gonna do it after this match. I'll start it in just a sec. No, this matrix exponentiation stuff is tricky. You should have started a while ago. It's due tomorrow. Huh? It's integers and exponents. I passed algebra. I don't think it's that bad. This is the practice problem? This seems super easy. Look, 1 to the 5th is 1, 2 to the 5th is 32, 2 to the 5th is 32, and negative 2 to the 5th is negative 32. Easy. Yeah, except this is the actual answer. They're nothing alike. This method doesn't work. Here, let me show you how it's done. All right, so this is how you do it. You use a technique called diagonalization. What that means is we're going to split this matrix up into 3 components. The first component, P, the second diagonalized component, D, and a third component, which is simply P inverse. To do this, the first thing we need are the eigenvalues. We do this by appending negative lambda to all the diagonal elements in the matrix. Then solving, setting the determinant for 0. Don't forget the extra term. After foiling these together and simplifying, we get the characteristic equation. And the solutions of this characteristic equation are our eigenvalues. In this case, it factors really nicely. So our 2 eigenvalues, we'll call them 1 and 2, are negative 3 and positive 2. I'm going to put these up here so we don't lose them. The next step is to use these eigenvalues to get our eigenvectors. So we'll start with the first eigenvalue. I plug it in for lambda. Remember, there's already a negative sign there. This gives me the resulting matrix 4, 2, 2, and 1. Then I append a column matrix of zeros and solve the resulting system. These are similar, so I could choose either one. I'll get the same answers. I'll choose the bottom one because it's slightly simpler. Doing some subtraction, I get y is equal to negative 2x. Now there are an infinite number of eigenvectors that satisfy this equation, so I'll just choose the simplest one. 1 and negative 2. So I'll put that up here. It's important to remember which eigenvector came from which eigenvalue, because the order matters when we put them together. For the second eigenvector, we do the same thing with the second eigenvalue. 1 minus 2, and negative 2 minus 2. This gives us the resulting matrix, negative 1, 2, 2, negative 4. I append the column matrix of zeros to it, and solve the resulting system. Again, I could choose either. Negative x plus 2y is equal to 0. Some subtraction gives us 2y is equal to x. The simplest one of these, I think, is just 2, 1. So for our second eigenvector, we get the column vector 2, 1. Now we need to put these together. Matrix P is simply the eigenvectors in order together. So 1 and negative 2, right next to 2, 1. The D matrix simply has diagonal elements that are equal to our eigenvalues. In this case, negative 3 and 2. All other elements are 0. To get P inverse, we just take the inverse of P. To do that, we need a determinant, which will be 1 times 1 minus 2 times negative 2, which gives us 5. The formula for the inverse is 1 over the determinant, in this case 5, times the elements swapped. You swap these two and switch the signs on the others. So our resulting inverse matrix will be 1 over 5, negative 2 over 5, 2 over 5, and 1 over 5. That is our P inverse. So let's put it all together. We've said this original matrix is equal to these three things multiplied together. So why is this useful? Well, say we wanted to multiply the matrix by itself over and over again, this exponentiation. If I do that, something interesting happens. No matter how many times I end up multiplying, these p's and p inverses end up canceling, because as we know, any matrix times its own inverse is equal to the identity. So this subset here, and as many as I have will simply cancel. So this leaves us with our opening matrix P, as many D's as we have. In this case, it would be 5. And our final matrix, it doesn't cancel, P inverse. Or the easier way to write this, it becomes matrix P times matrix D to the n, however many matrices you have, times P inverse. Now this is important. You might think it put us right back where we started, but actually, because D is diagonalized and it only has diagonal elements, that means that in order to take the exponentiation of it, all I have to do is apply the exponent to each diagonal piece. This is very important when you're dealing with large exponents, because it saves you a lot of time, but also because you can do this with fractional exponents or complex exponents, things you normally couldn't do normally. So let's put it all together. Our final answer will be our matrix P, 1, 2, -2, and 1, times our matrix D to the 5th, which will be -243, 0, 0, and 32, times our P inverse, which is 1 over 5, -2 over 5, 2 over 5, and 1 over 5. And that will equal our original matrix to the 5th. All right, to summarize the method for diagonalization of the matrix. Step 1, find the eigenvalues. You do this by subtracting lambda from all of the diagonal elements, then solving for the determinants at equal to 0. Step 2, use the values you found in step 1 to find the eigenvectors. You do this by appending a column matrix of zeros and solving the resulting system. Step 3, the eigenvectors together will make the matrix P, order matters, and the eigenvalues are the diagonal elements of matrix D. Step 4, find the inverse of P, then exponentiate D if necessary. Combining all that together is diagonalization. So, you think you got all that? Oh, yeah, I just threw it into Chegg. Got the answers that way, it's no big deal. You know we have an oral exam tomorrow, right?